First of all, thanks to Giovanni for giving me the opportunity to present this work. So today I will present some recent work that we carried out on the electric field manipulation of perpendicular magnetic anisotropy in platinum cobalt oxide multilayers. So this work is the result of a long-standing collaboration between our group in INSTITUT and a SpinTech group, which are our neighbors in Grenoble. And I would like to acknowledge in particular my postdoc, Ayman Mafasatwi, who made most of the experiments that I'm going to present today. And I would like to thank also Anne Bernard-Montel, who actually initiated this work a few years ago in INSTITUT, and from whom I actually inherited this subject when she left for the University of Toulouse a few years ago. So electric field manipulation of magnetic properties is a field, a relatively new field that is actually been pioneered in Grenoble in our group by Dominique Givor, who left us a few years ago actually. So they first demonstrate in the case of thin iron palladium and iron platinum films the possibility to change the magnetic anisotropy by a few percent using electric field, in this case using a liquid electrolyte. More recently, still in our work, this was the work of Anne, it was shown that the electric field would be used to change the balance between Jelinsky-Bohr interaction, dipolar interaction, and perpendicular magnetic anisotropy to switch the platinum cobalt aluminum between a state in which magnetic skyrmions were stabilized, here with minus 20 volts, to a state in which the skyrmions were disappeared, so what they called the skyrmion switch. So in most of the recent works that you can find in literature, the manipulation of magnetic anisotropy was carried out through electronic effects, so charge accumulation at the Fermi level. This effect, as confirmed by Van-Strach calculation, is quite small and can give rise to changes of the coercivity or of the perpendicular magnetic anisotropy of just a few percent. More recently, it was demonstrated that using magnetoionics, much larger effects, much larger variation of the anisotropy can be obtained. This was first demonstrated by the Beach group in the case of platinum cobalt by layers, gadolinium oxide layer, here 30 nanometers. And in this case, you can see that they could switch the magnetization from totally out of plane, the square loop, to in plane. So this is a huge change of anisotropy, much larger than the previous works. This was also done by other groups. And in this case, the effect was shown to be non-volatile, so the magnetic properties were kept after the removal of the electric field, and it was also shown that they were depending on the time of application of the electric field, and this led them to propose that this change of anisotropy is related to the migration of ions in the gadolinium oxide layer that acts as an ionic conductor. In the work that I'm going to present you today, we had a slightly different approach. So we started with our favorite model system, which is a tri-layer of platinum cobalt with a thin layer of oxide. In this case, in the case of this work, we used aluminum, magnesium, and terbium oxide. And we first optimized the magnetic properties, we optimized the structure of the tri-layer to obtain the desired magnetic properties. In this case, we wanted the anisotropy to be close to the in-plane to out-of-plane transition. So typically the cobalt layer is about 1 nanometer thick, and the oxide layer is about 1 nanometer thick also. I have to say that we have been working on these tri-layers for many years, but not only for the large perpendicular magnetic anisotropy, but especially in the last 10 years since it was discovered, as you know, a large interfacial Jarinsky-Moore interaction in these systems, which gives rise, of course, of chiral Néel-Waals and of skyrmions. And we have been very busy trying to understand current and especially field-driven domain wall dynamics in these systems, which is strongly modified by DMI. But today I'm not going to talk about DMI, I'm going to talk about electric field. I come back to our system. So we start with this platinum cobalt oxide tri-layers. And then on top of it, we deposit a high K dielectric layer. In this case, in this work, it was a zirconium oxide deposited by atomic layer deposition, which acts as a dielectric and also as an ionic conductor. And then we use platinum electrodes, local platinum electrodes that act as an oxygen electrode. So, so the first, so in order to explain how the ionic migration can can help tuning the magnetic anisotropy. So I wanted to show you what we know about magnetic anisotropy in these tri-layer systems. And this was actually the work pioneered by the Spindel group about 20 years ago. So in these systems, so what we know is that the strongest source of magnetic anisotropy is situated at the platinum cobalt interface, due of course to spin orbit interaction, to spin orbit effects. But what was found is also the presence of an anisotropy term at the interface between the cobalt and the metal. In this case, I show the case of aluminum. And what was shown is that this anisotropy term depends strongly on the oxidation of the cobalt oxide interface. And has this characteristic shape that can be found in any kind of oxide layer. So for example, here in the case of platinum cobalt alumina with 0.6 nanometers of cobalt, so if the aluminum is not oxidized, the magnetization lies in the plane. When the aluminum is oxidized, you can see that the anisotropy was found to increase. The magnetization turns out of plane, it reaches a maximum anisotropy for some oxidation rate, after which the anisotropy decreases and it reaches either an in-plane orientation or a demagnetized state. Well, in 2008, we found out through XPS measurements that this maximum anisotropy was associated to the situation where at the interface between the cobalt and the oxide of the cobalt and the aluminum, most of the cobalt-aluminum bonds were gradually replaced by cobalt oxide. So where the PMA is maximum, we have the cobalt that is completely covered by a layer of oxygen, after which we call this the overoxidized state, the anisotropy starts decreasing. So this dependence of the anisotropy at the top cobalt interface from the rate of oxidation of this interface can explain how the oxygen migration can tune the perpendicular magnetic anisotropy of these systems, as was shown before by the Beach group. So in this work, the idea was to try to extend the work that was done by Anne-Bernard Mantel on platinum cobalt aluminum, in which skyrmions could be switched on and off by an electric field, to extend this work to much smaller skyrmions. And this was done in the framework of the DARPA project on skyrmions. So we worked on platinum cobalt MGO. That is a system in which magnetic skyrmions had already been observed at room temperature. So this trilayer was covered by zirconium oxide, as I told you, 10 nanometers thick zirconium oxide. So with about 1 nanometer of cobalt in the virgin state, you can see this red, sorry, this black hysteresis loop that is characterized so with zero remnants. Now it won't have the, okay, my mouse. That is characteristic of a demagnetized state. When we apply a negative voltage, I keep losing my, sorry, I keep losing my mouse. When you apply a negative voltage for 30 seconds, you can see that this hysteresis loop becomes square, which indicates a strong increase of the perpendicular magnetic anisotropy. So this effect is non-volatile, so if we remove the electric field, the magnetization stays perpendicular, and this suggests us that the microscopic mechanism resulting in this change of anisotropy, increase of anisotropy, is the migration of oxygen ions within the zirconium oxide layer down to the cobalt interface. And this is driven by this negative voltage. And this is in agreement with what we know about our system. It was prepared in an under-oxidized state. And so, sorry. So an increase of the oxidation would lead to an increase of the anisotropy. The MFM measurements, images that you can see here, they show that in the initial state, there is the presence of this stripe labyrinthine domains with a periodicity of about 200 nanometers. And this can be transformed into magnetic skirmings with the application of a weak autoplane magnetic field. Of course, if you apply the negative voltage to increase the anisotropy, the skirmings disappeared. And with, we were very disappointed to see that when we applied an opposite electric field, so here a positive electric field, we could not recover the lower anisotropy, so we could not show this reversible creation and annihilation of the magnetic skirmings. I don't have time here to explain the details of how do we explain this irreversibility, but if you are interested, we have just published, well, actually it's almost published this paper in Physical Review Applied. So the next system that we worked on is platinum cobalt aluminum oxide, again with 10 nanometers of zirconium oxide deposited on top, and the platinum electrode. So in this case, the cobalt thickness is only 0.6 nanometers, so that the sample has a stronger perpendicular anisotropy, so it has this square loop. By applying a positive electric field, you can see the gradual decrease of the coercivity that we associate to a decrease of the perpendicular anisotropy. And again, in this case, we have the same non-volatile effect, which can be explained by the migration of oxygen ions away from the cobalt oxide interface, which decreases the magnetic anisotropy. If in this case we have a reversible effect, because when we apply an opposite electric field with a negative bias voltage shown here, we can recover slowly and gradually the strong perpendicular anisotropy and a state that is practically identical to the one that we had before the application of the field. So in this case, we have non-volatile and reversible effect of our bias voltage. So here we show with these Kerr images that the change of anisotropy induced by electric field gating can also change, is responsible for the change of magnetization reversal mechanism. So at the beginning in the virgin state, the magnetization reverses via the expansion of a few domains that are nucleated outside the electric region here. And as a positive voltage is applied, you can see that the mechanism of reversal mechanism is now dominated by the nucleation of a large density of domains, and its density increases as the voltage as the application time of the voltage, the gate voltage is increased. And this is, can be explained by the decrease by the presence of a low anisotropy and a large dispersion of nucleation fields, as expected by the fact that the electric field decreased strongly the anisotropy. So now if you apply the opposite bias voltage for increasing times, we slowly recover the stated with the reversal mechanism that we had at the beginning. So in this case of platinum, cobalt, aluminum, we were able to evaluate quantitatively the electric field efficiency, which is given by this value, so more than 1000 femtojoule per volt per meter at room temperature, and these values are comparable to the best values found in the literature that were, however, done at higher temperatures. The next system we worked on is platinum cobalt terbium oxide. In this case, the cobalt was deposited with a gradient of thickness, so between 1.1 and 1. Some nanometers. And here I'm showing the results for 1.1 and 0.22 nanometers of cobalt. So in both cases, the initial state, the magnetization lies in the plane. So it's this black hysteresis loop here. And you can see that in the case of 1.2 nanometers, a strong minus 9 volts gating was necessary to switch the magnetization out of the plane, this red loop. And then a similar opposite voltage was necessary to, was sufficient for obtaining this stripe domains structure, this butterfly hysteresis loop that is probably due to a stripe domain structure. But if we decrease the thickness of the cobalt to 1.1 nanometer, we can see that the same switch of anisotropy from in-plane to out-of-plane can be obtained with a much lower gating. Same for the switch between the out-of-plane to these butterfly loops. And this dependence on the efficiency of the electric field on the thickness can be explained by the relation of the magnetic anisotropy, the dependence of magnetic anisotropy on the thickness. So we're talking about interfacial anisotropy. So in the first case of 1.2 nanometers of cobalt, the two anisotropy terms at the platinum and the oxide interface are lower because of the higher thickness, and then a larger variation of the anisotropy, so of the oxidation of the top interface of the cobalt, will be necessary to recover the out-of-plane anisotropy, so to overcome the dipolar term that is the same in the two systems. So here we also showed that not only the efficiency can be tuned by tuning the thickness of the cobalt, but as expected, by increasing the temperature of the system during the application of the electric field, the ion migration can be enhanced, and the lower voltages will be sufficient to obtain the same change of anisotropy. So in the case of, in the case of platinum cobalt terbium, we also showed, we give a clear demonstration of the fact that the perpendicular magnetic anisotropy changes depending on the time during which the electric field is applied. So here are MFM measurements, MFM images. So in the first one here on the left, the initial state in magnetization is out of the plane. We then apply a positive voltage for 10 seconds, and you can see the formation of these stripe domains, which show the decrease of anisotropy and the approaching of the spin orientation transition. In this case, we have a periodicity of about 500 nanometers. If we increase the application, if we apply the gate voltage for another 30 seconds, you can see that the periodicity of the stripe domains decreases strongly down to some 100 nanometers, and this is this is due to the, but this can be explained by the fact that the periodicity of the stripe domains depends exponentially on the domain wall energy, which is decreased if the anisotropy is decreased. So in my final slide, I wanted to show you that, so up to now, I've shown you that we have used the electric field to manipulate the perpendicular magnetic anisotropy only in the under-oxidized part of this PMA curve, so between the under-oxidized state and the maximum anisotropy. So in the case of this platinum cobalt terbium, we also show that the electric field can be used to manipulate the anisotropy to go from the under-oxidized state and to go also beyond the maximum anisotropy down to the over-oxidized state where with in-plane anisotropy. So what I show here in this curve, I show the variation of the coercivity of the sample as a function of time, application time of the electric field. And this was done with a constant field by taking a hysteresis loop every 4 seconds. So you can see here, for example, for the larger gate voltage, we have a fast increase of, actually here I start from the over-oxidized state with in-plane anisotropy. As the gate voltage is applied, you have first this fast increase of the coercivity up to the maximum anisotropy, and then a slower decrease of the anisotropy after the sample has been after the sample is well, after the maximum anisotropy. What you can see with a slower decrease after the maximum. What you can see here is that this variation of the anisotropy is accelerated as the voltage is increased. And I've plotted here the time necessary for switching between in-plane and out-of-plane magnetization. And you can see clearly that there is a strongly non-linear variation of this time as a function of the gate voltage. So this is a sort of exponential variation of the switching time as a function of the voltage. So this can be explained by the nonlinear drift velocity of ions that is expected for large fields. This was actually calculated recently in this paper for titanium oxide. Sorry. This exponential variation of the drift velocity is expected for voltages beyond 10 to the 7 volt per centimeter, that is equivalent to the voltages that the electric field that we are using here. So with this, I wanted to say that so this magneto-ionic way to manipulate perpendicular magnetic anisotropy, of course, is not a fast effect, because I've shown you we have always used more than tens of seconds to switch the magnetization from, for example, in plane to out of plane. But by optimizing the thickness of the cobalt and the thickness of the, actually also the thickness of the zirconium oxide, so of the ionic conductor, we can hope to get to reasonable times that can be of the order of some milliseconds. So with this, I conclude my talk. So I've shown you that strong electric field effects have been obtained for in platinum cobalt oxide layers using zirconium oxide as the electric layer. And no matter the nature of the oxide, this mechanism is working. We have seen that the effect is non-volatile and reversible, and we have shown that the strength of the effect depends on the application time of the electric field, and this is coherent with the oxygen migration modifying the rate of oxidation of the cobalt top interface. So we have seen that the effect is slow, but it could be optimized by increasing the voltages and reaching the regime where the ion drift velocity is nonlinear. And for the future, we would like to optimize the energy cost of this effect by optimizing both the electric layer and the cobalt thickness. And we would like to show the reversibility of the small sperm nucleation in the case of in the case of small skirmins. And I thank you for your attention.